You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to be shining a light on some of our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. The role of easy and robust RF front-end solutions in IoT applications is growing. In today's technology, multi-layer chip antennas are a preference for engineers who are restricted by cost, time, and space requirements in wireless system designs for handheld devices that seem to be getting smaller. These antennas are extremely low profile, very light in weight, they have low losses, and they're still able to achieve relatively high gain thanks to LTCC-based technology and are frequently used in RF applications for wireless transmission of data. Today's podcast is a webinar presented by Mohammed Ali Khalid, product manager for EMC inductors and RF components here at Worth Electronic. During this presentation, Mohammed will explain how even the non-RF engineers can easily incorporate the antenna into their design without having special design knowledge. We'll also discuss how to match chip antenna with the rest of the circuit with the help of RF inductors and capacitors for the optimal performance. And then we'll finish with the RF portfolio from Worth Electronic. Enjoy today's Worth Electronic What's Up podcast with Mohammed Ali Khalid and antenna matching network optimization and the effect of coaxial connectors.
We will start with the IoT and different kinds of antennas being used in IoT. Then we move on to the antenna matching and passive elements. In the end, we will talk about coaxial connectors and their impact on impedance matching. This section will also include the simulations and TDR analysis. More or less everyone is familiar with the term IoT that we keep hearing again and again. The IoT, or the Internet of Things, refers to the billions of devices around the world that are connected to Internet and are able to collect and share data. The applications are numerous and widespread across many different sectors of life. Some of the examples include our homes, healthcare, environment monitoring, etc. Here is a fun fact about IoT, that the IoT existed even before the internet. This vending machine that you see in the picture, the students from the CMU, the Carnegie Mellon University in Pennsylvania, were able to track the stock of the drinks or sodas, and they could tell how many bottles were left in the vending machine remotely. This happened in 1982, well before the advent of internet, and ARPANET was used at that time to enable the communication. Whenever we talk about the IoT, we also have to consider antennas. Antennas are a key component necessary for connection between devices. As the IoT devices grow smaller in size, the optimal antenna design is proving to be difficult. Depending on the size, cost, and design effort, the engineer has to choose the best antenna. Now, here are the three most common types of antennas that are being used for communications in IoT devices. The wire antenna is low cost and has very simple design, but it's simply too big. Normally, the PCB only has small space available. Then comes the PCB or trace antenna, which shows good performance in terms of gain and efficiency, and is a relatively smaller in size to wire antennas. But the downside is that it needs RF expertise for design and implementation, and not all the companies who are designing smart devices have RF front-end designers. The chip antenna is smaller in size and easy to integrate, which makes it the ideal candidate for small IoT devices. But it always needs a matching circuit if we want to achieve better performance. Here I would also like to mention that the Worth Electronic also offers this antenna matching service, and if you are looking for one, then we will be able to help you. A chip antenna is basically layers of metallization printed on the ceramic substrate. The layers are then put together to form a helical-like pattern in most of the cases. Through this design, we get almost omnidirectional radiation pattern and very good size to performance ratio. Specially designed dielectric material is used as substrate in chip antenna with varying dielectric constant. So it could be anywhere between 6 to 10 in most of the cases. Placing the antenna on the PCB is a little bit tricky since the antenna is the product of its surroundings. Most important thing to remember is that the antenna is placed on ground-free area, away from the rest of the circuit components. Here, W is the width of the antenna and L is the length of the antenna. It should be made sure that nothing is placed close to the antenna that can affect its near field, because the changes in the near field means change in the antenna impedance, which can lead to performance degradation. Now we will talk about antenna matching, but before we need to review one important concept, which is called characteristic impedance. We all know that impedance is the amount of opposition faced by the RF signal. For optimal performance, source impedance should be equal to the load impedance, which in turn is the characteristic impedance. This can be explained with the help of this water pipe analogy. For the smooth flow of water, the diameter of two pipes should be equal. But if the diameter of second pipe changes due to some reason, all of the water will not be able to go through it, unless we implement a certain transition pipe design whose diameter can match both pipes. This is the function of a matching circuit. I think we are well familiar with this picture of Smith chart. It looks very complex, but once you get to know it, then it becomes your best friend. It is a very useful tool for RF engineers who are working with complex impedances, as it can be plotted, as the impedance can be plotted on the Smith chart, which is then used for the calculation of the matching circuit. So here is the small detail of how the components move the impedance in the Smith chart. So normally a matching circuit consists of inductors and capacitors. So if an inductor in series or capacitor in series or inductor in parallel or capacitor in parallel. The goal here is to bring the impedance to the center of Smith chart, which is the 50 ohms point. I will not go too deep into the Smith chart itself since there are many free online tools that can help you with plotting this impedance and calculating matching circuit. Here is an example of a Bluetooth Wi-Fi chip antenna working at 2.4 gigahertz. And below the graph, you can see different matching circuits that were used. And as you can see, they result in very different return loss measurements. So with the help of matching circuit, we can control the bandwidth and the resonating frequency of the antenna. Now we will discuss the passive components used for antenna matching. Here are the ideal models for inductor and capacitor. The impedance changes linearly with the frequency as expected in the ideal case. In the real scenario, we have losses in the circuit represented by Rs. Losses can also be quantified by Q value, which is called the quality factor. Higher Q means low loss and vice versa. This loss becomes very prominent at higher frequencies. So as the frequency gets higher, the wavelength gets smaller. To this small wavelength, the coils of the inductor and the air between them looks like a capacitor. Hence, we have a parasitic capacitance problem. At some point, this capacitance effect becomes so great that it is equal to the inductance of the inductor. This point is called the self-resonant frequency. A good rule of thumb is to use those inductors whose self-resonant frequency is 10 times higher than the operating frequency. Here is the equivalent series and parallel circuits of capacitor considering the losses. The losses can be quantified with the help of quality factor. Again, one interesting thing to note here is how the losses increase and the Q factor decreases as we go higher in capacitance and frequency. So there are three most common types of matching circuits used with chip antennas on the PCB. Higher the number of elements, higher the freedom for matching. So one can argue that we can have better matching if we have higher number of matching elements. But pi or the T circuit with 3 elements is the most optimal solution. Because there can be higher number of elements, but then it becomes complex and expensive. So it is not very desirable. And the most common size that we use for antenna matching is 0402. There are bigger and smaller sizes available for RF inductors and capacitors. Of course, the smaller size can be 0201 and the bigger size can be 0603. But bigger size means huge parasitic impedance. That's why the matching components tend to have smaller sizes. Then one can argue that why don't we use 0201 size? That's simply because it's too small. So when we are doing the antenna matching, we need to solder and desolder the components by hand most of the time, and it takes a lot of iterations. So soldering a 0201 size inductor or capacitor is not very easy. Now we come to the last part of the webinar and talk about coaxial connectors and their impact on the impedance. So these are the two most common SMA connectors, also called the edge launch connectors, being used at these frequencies. So you can see the effects from the different center pin design. So one connector has a round pin and one other connector has the flat pin. Usually the big round pin design is used for lower frequencies and the flat tap typically is used for higher frequencies. Why is that? Because the round post, which is bigger, fits better to the wider tracks just because of the size. And contrary to that, the flat tab is mostly used for narrow signal lines, which are often seen in 4-layer PCBs. Due to its very slim profile, and the flat tab brings less parasitic capacitance to thinner transmission lines. It needs to be handled carefully though, because it can be bent easily and it should be soldered with care, which means using the minimum amount of solder paste. Now we talk a little bit about discontinuities and TDR before we can jump into the SMA connector simulation and measurement. In this slide, you can see different cases of discontinuities can have different causes. For example, there's a geometrical or material change and it can result in reflections and field conversions. What is a TDR measurement? The TDR or time domain reflectometry measurement with network analyzer can be used to identify these discontinuities as it shows the impedance variation over time. In this graph, we can see the different impedance variations caused by the discontinuities, and these can be traced back to certain influences like changes from cable to connector or from connector to PCB. In the TDR, we will of course never have 100% straight line at 50 ohm. That is like the ideal case, and that never happens. We will have small influences and mismatches of impedance, but we want to stay as close as possible to the 50 ohm line. Now here we will talk about the connector, PCB and the transmission line interface and show the typical combinations between SMA inner pin style and PCB layer stack. What effects do we have to take into account when combining connector and the PCB? First of all, we see the discontinuity. Due to the change in material and the change of geometry, we get changes in line impedance and the field conversions. These effects cause huge mismatches and the reflections. To avoid this, the connection area has to be optimized by using planar matching circuits. This is a very important term, planar matching circuits. I repeat, and I will get back to it later on in the presentation. Now, sorry. Here you can see the electric fields of the grounded coplanar waveguide and the SMA connector. The geometry of the E field, the electric field, is different on the RF line of the PCB and then it is on the SMA connector. In the picture on the left side, we see the shape of the electric field in a coplanar waveguide with vias. Due to the vias, the radiation is minimized and the spread of the field is limited to a certain specific area. In our SMA connector on the right picture, we see different structure of the E field. It is pulsing from the surface of the signal pin to the inner surface of the shielding. using the full circle. This is very typical electric field pattern for the coaxial components. Now, when we solder the connector to the PCB, what happens? We can see the shape of the electric field that is spread quite far and has a different shape to what we saw before. As the geometry changes from circular to rectangular, the field starts to pulse between the signal pin and the ground pins. Thus, we can see how the fields are behaving in real time, and this data can be used to predict how matched or unmatched the connection is. Here is another example of SMA connector and transmission line behavior with two-layer PCB. The normal end latch connectors are limited to certain PCB thickness due to their geometry. So they are only available for 1.1 millimeter or 1.6 millimeter thick PCB. The above shown SMA connector can be an alternative to a standard end launch type if a thicker PCB is in use. But the frequency behavior of this hook type is different, so we need to adapt its layout to our needs. Now, three different designs are analyzed to see which one has the most stable impedance response. So the case 1. This is according to the initial datasheet layout, only two vias for the chassis pins, no further ground connection, and just normal arbitrary RF line according to the formulas, nothing special for the connector. We look at the TDR analysis. In the TDR measurement, we can see that we have too much impedance mismatch in the transition area. Afterwards, the system stabilizes on the transmission line. Remember, the goal here is to keep the impedance to 50 ohms. So case 2. We begin optimizing the design by adding two more vias to the ground and create a pad that ensures we have a good ground connection. We look at the result and we see a huge mismatch in the connection area before the impedance normalizes. So what is the reason for it? If we go back, because of adding the big ground pads for the ground pins, the connection area behaves now like a coplanar waveguide. The ground pads are also narrow. The distance between signal line and ground, and we know that this distance influences the impedance. In this area, we create a lot more losses than before due to this big mismatch. And in addition, our freeline adaptation to fit the connector was also not optimized. As we have a behavior like coplanar waveguide in this connection area, we need to respect this, and in our transmission line design, narrow the line in this area to get the right impedance. So what we are doing is tapering the transmission line in this specific area where it behaves like a coplanar waveguide. Additionally, we use a line taper to widen the transmission line when making the change from connection area to micro strip line. This is the matching circuit for transmission line that reduces reflections and losses. Smooth and curved shape transition is necessary for the success of this design. Now we look at the TDR analysis again, and as you can see, we have managed to improve the impedance response by changing the geometry of the connector and microstrip line interface. Of course, ideal would be if we are close to 50 ohm, but this small amount of variation, which is like few ohms, is okay in this design. So that's all regarding today's webinar. Now I would like to very briefly present our RF portfolio, which has been growing quite a lot in past few years here at Worth Electronic. You can see that we have majority of components for the RF front-end design. And you can get in touch with our sales team if you're interested in any of these products.
This podcast was taken from an updated Worth Electronic webinar. To view the materials and replay the webinar on demand, visit www.we-online.com/webinars or click the link attached in this podcast. You can also view the complete Worth Electronic RF portfolio, including antennas, filters, inductors, smart modules, and sensors, and more at worthelectronic.com. You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.